Alright, so in this video we're going to take a look at what acceleration is using the same data. So we can write down here acceleration is the rate of change of velocity. So think about how this is fundamentally different from the definition for velocity. Velocity is the rate of change of position. Acceleration is the rate of change of velocity. And the equation for it looks like this. A, acceleration, is equals rate, means we're dividing by a time interval, and then change of velocity, delta v. And that means delta v means v final, final velocity minus the initial velocity divided by some time period. Okay, so let's take a look at an example here. If we bring back that line that we used before. Okay, so if we bring back that line, where is it? And here we go. So I'm going to try to draw that line. Oh, there it goes. Okay, and try to move it into position here. There it goes. Okay, might need to tweak this just a little bit, not that way. Alright, well we get the idea. That's where I was going constant velocity, and actually I should even move this up a little bit more, like there. So we labeled before that this was constant velocity, and now we're going to take a look at this part here. I'm going to label this other part in green, and this part here is where it was accelerating. So we can label that accelerating. Now here's where we have to bring in this idea that we call instantaneous velocity. At the very beginning, the car was at rest. So it had zero initial velocity, initial instantaneous velocity. And we can see that the curve, the green curve, in fact, was flat at the very beginning. But it doesn't stay flat for very long, because if we keep looking at it after successive intervals, we can see that it keeps getting slightly steeper as we go, until finally the slope of it is equal to the slope of the blue part. So every one of these little slopes that we call in there, that I'm labeling, these are called instantaneous velocities. And there's actually no limit to how many of these little instantaneous velocities we look at, because it's a curve, the curve is constantly changing. But it might seem a little weird to you to think that you can talk about the slope of a line at a certain point of that line. So in here we can label instantaneous velocities. And our ultimate goal in the buggy lab, well, the way that we framed it was, let's find the top speed of the buggy. And so the top speed would be where it is the steepest slope. And we can see that it is this steep slope from this point forward. And I'll put a little line there. From that vertical point forward is constantly the same slope, and it's the maximum slope. But it takes a while for the slope to build up to that. It takes a while for the velocity to build up to that. Okay, so all these ones that we just drew here, all these little black, those are also instantaneous velocities. But because the velocity isn't changing, we could say that the instantaneous velocity here is the same as the instantaneous velocity up here. Now, in terms of actually calculating the rate of acceleration of the car in this particular example, we can say that the initial velocity, so if we throw in some numbers here, if we say the initial velocity is 0 because it was at rest, it started at rest, or we should say even from rest. Actually, I'm going to erase that. Okay, so let's try that again. So we can say 0 because it was at from rest. And the final velocity that it got up to, we calculated that above. What was it again? It was 3 1/3, 3.3 we'll say. So that was 3.3, and that's 3.3 minus 0. And so what we have on top there is 33 minus 0, which is 33. And remember, the units for that were centimeter per second. This is going back to our previous example with velocity. And we're dividing by a time interval. Now here we need to look at the time interval. How much time did it take to accelerate? It went from time 0 all the way up to 4 seconds. And at that point we said it reached its top speed. So here the time interval is 4 seconds. So we can just divide this by 4 seconds. And what we'll get is, that was supposed to be 3.3. 3.3 divided by 4, 3.3 divided by 2 would be 1.65. 1.65 divided by 2, again, would be 0.825. 0.825. And just given the precision of what we're doing with our measurements here, we're reading these numbers off of these numbers that we're getting from the graph, and I don't think we know the precision of those to any more than 2 sig figs. So we're going to take our 0.825 and round that to 0.83. And now let's look at the units. I'm going to scroll this up for us. The units we have, and I'll circle these in blue. We have centimeters per second divided by seconds. So that's going to give us units of centimeters per second square. That can be a weird thing to think about, centimeters per second square for the units. So let's just look at that for a minute here. We are saying centimeters per second divided by second again. And we could actually write this like this. We could write it as centimeters per second, and rather than dividing by a second again, we can multiply it times 1 over second. So all I'm basically saying is that this here, dividing by a second, is the same as multiplying by 1 over second. And so hopefully now you see a little bit more clearly why we can, when we multiply these, just say centimeters over seconds squared. Okay? So that's kind of a little thing on the side there as far as the units working out. And I probably should have done that in black because it was about units. Okay. So I guess actually let's do this now. I'm going to erase this away just to give myself some more space, and let's actually formally do those units. So here we go. Velocity on top is centimeters per second. Typically we actually see meters per second. Of course you can do centimeters, millimeters, whatever. And the SI unit for time is seconds. And so for the SI units for acceleration, we get meters per second square. Okay, and again, as you're getting used to the color coding here, black, let's label those units. Okay, so before we move on, or before we conclude this lesson, I have 2 questions for you, and I hope that's clear enough for you to see. This is data taken from a group in period 4, and from the buggy lab. So my question for you is, which car has the greatest top speed? The green, the purple, the red, or do they all have the same top speed? And the way you're going to answer this is by clicking on the link to take you to the Google Doc. And here's the free response question that I'd like you to answer, also in that Google Doc. What was the rate of acceleration of the red car as it accelerated to its top speed? And so I'd like you in the Google Doc form to explain how you got your answer, show your work and explain. And the last question you'll see in that Google Doc form is, what questions do you have from this lesson? And we can talk about your questions tomorrow. All right, scholars, thanks for tuning in. I'll see you in class.